Like all statements, quantified statements can be negated. They have an opposite. That is, there is a statement that is true whenever our quantified statement is false, false whenever our quantified statement is true. Figuring out what the negations of these statements are has been one of our purposes in developing this Euler diagram equipment, and has been the reason that we want to include all of the weird possible diagrams. So we've seen that there are 5 possible diagrams. If we have 2 circles labeled A and B, we might have the B circle inside the A circle. We might have the A circle inside the B circle. They might be the same circle. They might be separate circles that overlap, and they might be separate circles that don't overlap. Right? Those are all the possibilities that we saw among Euler diagrams. And when you think about it, that's really all of the possible ways to put 2 circles together. So when we go to negate a quantified statement, we want to look at this list of possible diagrams, see which ones are compatible with making the statement true, throw those away. Whatever statement defines what's left, that's the negation. Okay, so let's start with a statement. We have the statement, all trees are tall. We'll let A represent the trees, and B represent the tall things. Okay, let's look back at the diagrams and see where that's true. All trees are tall. A is trees. B is tall things. So if all trees are tall, then we could have the A circle totally inside the B circle, right? All of the trees are tall. Or we could have trees and tall things being the same. Over here, we can't have this because this would be a tree that's not tall. This would be a tree that's not tall. This would be a tree that's not tall. Okay, so if all trees are tall is true, we could have diagrams 2 or 3, which means that the statement is false in all the other diagrams, in 1, 4, and 5. And in those diagrams, what did we see? Well, we saw trees that are not tall. They're here in diagram 1, here in diagram 4, here in diagram 5. What do all of these have in common? These are exactly the diagrams where some trees are not tall. So the negation of the statement, all trees are tall, is the statement, some trees are not tall. Okay, so that's how this works, right? We're gonna go through the diagrams. We're going to see which ones make the given statement true, and then which ones make the given statement false. How then would we negate the statement, some dogs can talk? Well, we go to our diagrams again. We'll let A represent dogs and B represent talking things. I'm going to go to a new copy of the diagrams. A represents dogs. B represents talking things. And we know that some dogs can talk. So in this diagram, do we have dogs that can talk? Yeah. In this diagram, do we have dogs that can talk? Yeah, they're right here. In this diagram, well, yeah, all the dogs and all the talking things are the same. In this diagram, The dogs that can talk are right here. But in this diagram, we don't have any talking dogs. Some dogs can talk are true in almost all of the diagrams. Some dogs can talk is true in all of diagrams 1, 2, 3, and 4. And that's why we had to include those weird cases. The statement is only false in diagram 5. That diagram where nothing overlaps, that's the negative universal, right? The negation of some dogs can talk is no dogs can talk. So, whenever you're trying to negate a quantified statement, this is the technique to use to figure out what to do, if it's not immediately intuitively obvious. Look at the 5 possible diagrams, see which ones make the given statement true, then the negation is the statement that is true in the rest of the diagrams.